Cool, we are live. Alrighty. Any questions other than the mysteries of CTC Link and 223? 223 will not fill up. I mean, I'll always let students in. So it's not like you absolutely have to set your alarm and get up early to get in. What is 223? 223 is Advanced Data Structures in Java. So it's the continuation to this course, and it's the completion of the 200 level CS sequence here at Clark. And it's the last course that you need in the CS sequence to be able to take junior level classes once you transfer. Is it prime? That's awesome. How about 220? Yeah, there's no 221. And 121 is not prime, but it's a nice square. Alright, so let's see. 223. Yes, 11 squared. Awesome. Yeah, I was not talking earlier. I was just muted. All right. So other questions? Everyone good on the ODP that you already finished? And 223 is a fun course. In this course, 222, we're learning, kind of the fundamentals of data structures. So we're building these things from the ground up, right? If you want to know how to take a derivative, you got to do the epsilon delta thing. Otherwise, you're just learning some mechanical procedure that doesn't mean anything. So same thing here. If you want to be able to work with a linked list, you really got to know what a linked list is, which means build it up from the ground up. Right, do the mallocs and adjust the pointers and that kind of stuff. When you work with trees, same idea there. But then in 223, in addition to continuing to learn new data structures, we also get to use some pre-existing classes, packages that make these things available for us. And so things like hashing and stuff, we just grab a whole package of utilities and we get to play the role of the user instead of the implementer, and use these to do all kinds of things, and we get into maybe a little bit of graphics and some networking and some threading and multi-threaded programming and some of the issues around that, and it's just all kinds of good stuff. So it's usually the funnest class of the sequence. It's a lot of work, but it's a lot of kind of instant gratification too. We make GUIs that pop up and have buttons and things like that. Real ones as opposed to kind of the fake ones in 224. So it'll be good. Alright, but you gotta get through PA3, so let's talk about PA3. So this is posted last night, way too late at night. And I decided not to go with the hash table assignment because I don't know why. It felt like a lot. There is a lot to hashes, but I kind of want you to dig down into stacks and queues. It's a nice follow-on from linked list because you're going to use linked list to implement these. Legal reasons. Oh, yeah. All right, so programming assignment 3. So you're basically going to build a package and implement stacks and queues using linked lists, and then you're going to make a main program wrapper around it so that the user can type commands and interact with your data structures. So let me show you what this looks like first, and then we'll talk about what it all means. So I'm leaving you a sample executable under /temp. It's called PA3. And this shows you what a correctly working program would do. This would get you 100%, assuming that the code is well written and all that kind of stuff. Alright, so I run this, it gives me a welcome message. Optional, give me a usage message in the beginning. A small set of commands. Basically, we are building a stack and a queue inside, and we can interact with those structures through this front end. The program is always sitting in one of two modes, stack mode or queue mode. Okay, so if I type a number like 23, I've just added that number to a data structure. What did I add it to, the stack or the queue? Depends what mode I'm in. You need to start in stack mode. Okay, so I've just added 23 to a stack. If I do 45, that's been added to my stack. If I do 56, that's been added to my stack. If I want to see what my stack looks like, I type the S command. And that shows me my stack. Here's the top of the stack on the left. And it's got a 56, the last thing I pushed, and then a 45 and a 23. And if I add 111, that gets added to my stack. There's no feedback when you add a number. Okay, just come back with a prompt. But if I do an S to show me the stack, it'll show me my new stack now, and you can see I've got a 111 in the top. If I do P, that will pop the top of my stack, so that should remove the 111. So I do a P, and it shows me the value that it popped off. And now if I look at the stack again, I can see that the 111 has been removed. If I pop two more times, I pop off my 56 and 45, all I've got is a 23. If I push a 99 and I look at my stack, there's a 99 on the top. So it's a basic stack manipulation, right? You type a number, add it to the top of the stack. You type a P, pop it from the stack. You type an S, show what's in the stack. If the stack is empty, say stack is empty. If you try to pop from an empty stack, print an error message. And you know, I can generate multiple errors, and I can still go back and add something to the stack, and you know, that's fine. So I'm using S to print my stack, but this is also a command I use if I'm in queue mode to get back to stack mode. So, and anything else other than a legal command gives you a help message. So question mark or anything else. So S moves into stack mode and displays the stack. If I'm already in stack mode, it doesn't change my mode, but it still displays the stack. So if you want to work with a queue, what do? We go ahead and we type the queue command. Now we're in queue mode. Alright, and there's my current queue. The head is over here on the left, the tail is on the right, the queue is empty. Remember, I'm going to insert on the right and remove from the left. So now if I type a number like 23, that's been inserted into my queue. And if I type Q, I can see what my queue looks like. It's got a 23. Let's add a few more numbers and look at the queue, and you can see the last number I added, 5, that's at the tail. The head of the queue is still the 23, that's the first thing I put in. And if I do P, which in queue mode says remove the head of the queue, that takes out the 23. And if I look at my queue, there's what my queue looks like so far. And I can remove the 1, the 2, and the 3, and now I've just got a 4 and a 5 sitting in there. So this is queue mode. Type a number, it gets inserted at the tail. Type a P, it removes whatever's at the head and prints it out. Type a Q, and it will go ahead and show me what's in my queue right now. Now if I type an S, now it makes sense. It says it's switching to stack mode, and it shows me the stack. And it's still got that 234 sitting in there. If I do a Q, there's my queue. So you have two separate structures. You've got a linked list for a stack and a linked list for a queue. And if you switch from stack mode to queue mode, the stack still exists. You're just not interacting with it for the moment. So here's my queue right now. It's got a bunch of things added to it. I can go back to my stack. I can go to my stack and I can say S and I can see what's in my stack. And I can switch between those as I like. And that's pretty much it, right? So S or Q, choose which mode you're in and show you the current contents of the structure. Typing a number adds it to the structure. Typing a P removes whatever is ready to be removed from the structure. Can we do a conditional where it only says switching to stack mode if you were in queue mode? I'm okay with that. And when I look at the stack, right, I want it printed with TOS for top of stack, an arrow pointing to the first number, which should be the number on the top of the stack, and then the numbers that are deeper in the stack. When I print a queue, I want to see the word head with an arrow pointing to whatever's at the head, all the elements separated by spaces, then an arrow pointing to the tail with the word tail. Yeah, don't think terms of service. We'll reclaim that acronym. But if you want to print out a 50-page end-user license agreement, no, don't do that. All right, and then big Q quits. Here's the embarrassing part, which is, do I actually have Valgrind issues? So Valgrind, with the user agreement, got half the credit only if I agreed to it. You never know. Valgrind should give you, the standard beginning up here, and then, right, no warnings, no weird messages. And when you exit, you have to clear up your data structures. So if you exit with stuff on the stack or in the queue, you need to free all the memory associated with those linked lists. Even if those structures are empty, if you have a Sentinel node, you still need to release the Sentinel node. And then you should get no memory leaks. All right, you've already done half of this assignment, right? If you've got your linked list code from PA2, assuming you didn't burn it in a bonfire, you've got half the assignment done because you got the whole linked list system. But you're going to have two linked lists at once, so if there was something a little funny in your linked list code where maybe you were using a global for the Sentinel or something, that's going to blow up here, right? You really need a linked list implementation where you can have, here's a variable that's a linked list, here's a variable that's a linked list. So proper init function and all that kind of stuff. You can burn PA2 because you got it on Git, right? So you can pull it back down. Or you can ritualistically burn it every night for extra purification. So you're going to need two Sentinel nodes, and that's really it. There really isn't a whole lot of other stuff like that. Queue list equals init, stack list equals init, and now you can do add parentheses queue list comma number or add parentheses stack list comma number, and it should all kind of work automatically. It'll really kind of tell you if you adhered to the whole abstract data type concept, and if you did this thing faithfully without evil globals and things like that. It should just kind of work, which will be really cool. So what you really need to do is two main pieces. One is the main program, which I suggest keeping for last, right? And two is the implementation of the stack and the queue. And we went through those a while ago, and we'll go through the algorithms again, but it's pretty straightforward, right? So you're going to need to add something to your linked list code to insert in the beginning and insert at the end. And those are, similar to your general add function, but a lot simpler. And I recommend keeping track of the last node on the list so that you don't have to traverse all the way down the list to do your insert. But if you do, that's okay. I won't take off points. But you're going to have to write code anyway. Alright, so this is under /temp/PA3. Go back to this and refer to it when you're working on your main program to make sure you're doing what you're supposed to do. Right? If you're not sure what should happen when you pop from an empty stack, just go ahead and run this and you know, go into stack mode and pop. That's what it should do. Alright, so ready for the details? So you create a program, implements a stack in a queue, processes user commands to manipulate these. Two distinct structures. Your program should start in stack mode. Okay, legal commands are S, print the contents of the stack on one line separated by spaces, top of the stack on the left, and then set the current mode to stack mode. Q, same thing, but with queue mode, I want the head printed on the left and the tail on the right. Don't mix those up. I will take off points if you mix those up. If you type an integer, push it onto the stack or insert it at the tail of the queue. If you do a P, either pops from the stack or removed from the head of the queue and print the thing that you popped or removed. And if the stack is empty, print an error message instead. Queue quits the program after freeing all memory. Anything else gives a usage message. Alright, so you have to implement these using linked lists, and you're using linked lists that are dynamically allocated. Don't use a PA1 array and you know, fix the storage. You got to use mallocs. You got to make this thing in memory. So it's got to be a genuine linked list. So for a stack, we're going to push by inserting right after the sentinel and pop by removing right after that. For queues, we're going to do the head at the sentinel and the tail at the end. So stack so let's see, the head is after the sentinel. Okay, so here's the sentinel node. For the stack, this is the top of the stack. So when you push something onto the stack, put it right here before the first node after the sentinel. So you don't have to search through the stack, you don't have to look for things, you're definitely not sorting anything. You're just basically setting your new node to point wherever sentinel points, have the sentinel point to the new node. For the queue, the first node is the head, the last node is the tail. When you want to remove from the queue, just take the node that the sentinel is pointing to, that's the value that you're going to return. And then change the sentinel to point where that was pointing and delete this node. To insert into the queue, you need to insert at the tail. So find the tail, make a new node, have the tail point to that. And this works well if you have a tail pointer that points out here. And so when you want to add a new node, you don't have to start here and move all the way down. You can just go ahead and say tail pointer next. I'm curious, my documents are looking pixelated to me lately. I got 1600 by 1200. I'm gonna try something. Hopefully this doesn't like break the universe. Well, that didn't break the universe. That might have. Okay, I'm not going to mess with it anymore. Yeah, we're good. All right, so Q, when you want to insert, add after the tail pointer. When you want to insert, when you want to remove the thing the sentinel points to. All right, since your lists are dynamically allocated, you should never run out of memory. I will not try to make your system run out of memory, but you should check anytime that you call malloc, make sure the return value is not null. And if it is, that's some kind of catastrophic failure. You're allowed to say, you know, system is out of memory, and you can exit at that point. Just don't do it falsely, right, so that I can still test your code. Any error conditions, right, don't do anything extreme. Don't, like, you know, delete the person's stack just because they made a typo or they tried to pop from an empty stack. Don't, like, free the memory or something like that, right? Assume the user's going to make user errors and respond to them as indicated and just continue. And definitely changing between stack and queue mode doesn't change anything that's already stored in your stack or your queue. All right, program structure. You've got a lot of creative freedom here. Okay, I'm not going to give you a list of functions with prototypes and specific requirements. Do what makes sense. Okay, I want to see what you come up with trying to modularize your code and organize it in a way that works reasonably. You are required to use linked lists in the style from PA2. But, you know, if you want to make your own linked list package again and you don't want to call your functions, you know, add and delete, and you want to call them something else, it's up to you. Okay? I suggest you stick to the linked list implementations from PA2, and I suggest the following functions for stacks and queues. Init stack, which will, you know, do whatever your linked list initialization is. Push, which takes an integer and adds it to the stack. Pop, which returns an integer, figures out what to do if you try to pop from an empty stack. A function that will tell you if the stack is empty, and a function to display the contents of the stack. And same thing for queue, right? Init, add, remove, see if it's empty, and display the queue. If you make these sets of functions, right, this would be your interface inside main. Oh, I forgot about a free memory one also. So yeah, make a free memory function. Your main program will basically just be calls to these, right? But if you figure out how you want to set this up first, right, make yourself a bit of a design document, figure out what functions you're going to use, figure out what you're going to pass to those functions, what's going to come back from them, what the side effects are, etc. Then you can start testing your data structures from, you know, a subset main program. In other words, make a main program which says, you know, stack equals init stack. Push a 5, push a 6, display the stack. Push a 7, display the stack. Print the value of pop, display the stack. Print the value of pop, display the stack. You can just hardwire some commands to test out this code. And then you don't have to be messing with, you know, parsing command line and trying to figure out what the commands mean and all that kind of stuff. And if you have bugs, right, and you've got a set of exercises for your functions in a main program, right, you can reproduce that prog just by running the main program. You don't have to put in input or anything like that. That's going to speed up your debugging. So my suggestion is, you know, figure out how you're going to do this, and then maybe start with a stack. It's a little easier than the queue. Start implementing these functions. Definitely do an init, which really is just, you know, initialization of a linked list. And then maybe do a push and a display. Right? Pop's only marginally harder than push. But, you know, do a push and a display. And now just write your test program. Initialize a stack, push something, print, push another thing, print, push another thing, print. That's plenty of stuff to develop and debug and work on. And once that's working, go ahead and add a pop. and then do some pops and displays, and then add something to find out if the stack's empty. And in your main program, when you get around to parsing and the user says pop, before you call pop, see if the stack's empty, and if it is, print a message, stack is empty. Otherwise, go ahead and pop, and then print out the thing that you popped. And then do the same exercise developing it for the queue. Alright, these are not complex functions. Okay, pushing into a stack is probably 3 lines of code. It's literally, you know, new node equals malloc, new node.data equals value, new node.next equals sentinel.next, sentinel next equals new node. Okay, it's 4 lines. Pop is similar, except you have to free the node after you pop it. And display stack is like, you know, printing the linked list. So these are not complex functions in terms of, you know, deeply nested conditionals inside loops, inside, you know, this thing or that thing. But there are a lot of pieces to this assignment, right? So you definitely want to start this early. I know I always say that, but it's always true. You want to start this early. Even though the pieces are not necessarily that complex, if you start this the day before it's due, it's going to be a really, really crazy day. So start early, build it up systematically, right? So that after doing these tests, right, these routines are rock solid. You're done, right? Never have to look at those again. Do the same thing for Q. Once you finish that, these routines are rock solid, done. Now start working on your main program, and there's going to be calls to this. And the interface, you know, is similar to what you've done in the other assignments. Print a prompt, get a command, parse it, do whatever you're supposed to do. Alright, deliverables. Complete implementation of a linked list based stack and a linked list based queue. That's the whole game plan there. Main program was just these operations, these routines, operating as described above and as demonstrated in class. And there's the sample executable. That's as demonstrated in class. I'm not asking you to demonstrate in class. Plenty of commenting. Okay, again for each function. Put them on separate lines, right? Here's the first input variable, here's the name, here's the type, here's what it is. Here's the second input variable, here's the name, here's the type, here's what it is, right? Make it really easy to see those. And you're going to have to figure those out when you're designing your stack and your queue implementation. So when you're figuring them out, yeah, maybe do it on paper so you make changes, but you want to type those into your code so that when you're trying to use these functions from other functions, right, you've got something right there which tells you, what am I supposed to pass here? Do I pass, you know, the stack comma value, or do I pass the value comma stack, or right? So do this while you're writing your code, right? List the inputs, list the output and return value, list what the function does, any side effects, any cautions, and so on. So all of that stuff. Comment block in the beginning of your program, comments throughout your code, proper make file. Okay, so the make file should create an executable called PA3, and it should include a make clean option. And the default behavior of the make file should be PA3. Everybody's make files have been awesome so far, so just keep doing what you're doing. Source code, make file, any other relevant files, but do not give me any compiled files. Put them in a GitLab repo named stacks queues, uppercase S, uppercase Q. Add me as a reporter. Alright, as usual, you have a 24-hour offer to let me test your repository. If you send me an email before noon tomorrow and say, hey, I've made my repo, I've added you as a reporter, can you see if it works? I will download it and I'll let you know. Alright? If not, you can take your chances. If you know how to do this, don't worry about it. Oh, you forgot to send the email last time. Okay, don't forget to send the email. All right, grading, everyone's favorite part. So if it's not downloadable by the deadline, 20 points off. You have 24 hours to make it available. If I can't compile it, if I can't run it, if it seg faults right off the top, right, it's going to be a minimum 40 points off. Because then I have to go in and I have to start fixing your code so that I can test other pieces of it, which I'll try to do, okay, but make sure it runs. If it's not, implementing stacks and queues, if it's not using dynamic linked lists and so on, that's a 0. So make sure you're doing the assignment. Specific points, okay, your proper makefile, 5%. Being able to push and pop from the stack, 10% each. Okay, relatively minor functions, but, big chunk of the grade. Being able to add and remove from the queue, 10% each. Being able to correctly switch from one state to the other, 10%. Keep in mind, though, with these grading rubrics, right? For example, if there's no way I can get into queue mode, then I'm not going to be able to give you points for queue add and queue remove. So if you say, I'm not going to bother with the state switching code at all, right? You'll lose 10 points for that, but you might lose more points, right? So I need a way to test your stack, push, pop, to test your queue, remove, and add, and so on. But if you're switching correctly between modes and you're showing me the contents of the stack, okay, switching between modes, 10%. Printing the correct queue and stack contents following the stack or queue command, 10% each. Main program working as required, so all the requirements of that, the commands are right and so on, that's 10%. And then the niceties, right? Clean compilation, no warnings under the standard GCC command, 5%. Commenting before each function, 5%. Comment block in the beginning, 5%. Comments throughout code, 5%. And then consistent indenting, 5%. And that's your grade. All right, so that's a fair bit to digest. It's a 3-page assignment, but with what we've done so far, any questions on this? The way I implemented PA3, if I type an integer followed by something that's not an integer, it just goes ahead and accepts the integer as valid. That's okay. If scanf likes it, I like it. So that rule applies. But if you type something that's not an integer, like, ha ha ha, right, that should give you an error message. I just noticed a Cooler Master logo in the bottom left corner. Where is that? I'm guessing that's not on me. On my screen. Really? Huh, I'm missing it. Enhance. Okay, I'm lost. Computer, zoom, enhance. Alright, I think that might be coming from Zoom. Zoom is one of those things like Canvas. I have very little actual idea what the student experience is, which is disconcerting sometimes. All right, any other questions? So look that over, think about it, and then bring questions to class tomorrow. All right, let's finish up hashes. Let's talk about iterators a little more. So we had this idea of wanting to look at the contents of a hash. And the challenge here is that the hash doesn't have, you know, sort of a natural first, second, third element. And so we can't just say, you know, show me element 0, 1, 2, 3 of the hash. We index the elements with the keys, but the keys could be anything. They could be names, they could be binary code. And so unless we know what the keys are, how can we ask for the value associated with a key? So we have this idea of an iterator, and it might look something like this. And this is a more general concept. So we might have some start function which says I want to begin iterating through the contents of my structure. We might have some Boolean function called hasNext, which tells us, is there anything else to iterate through? And then we might have a next function which gives us the next thing in the iteration through our structure. So if we're doing this for our hash, right, itNext would return a key, and hasNext would return a yes or a no, like a 1 or a 0, and itStart doesn't really return anything. And so in our main program, let's say we want to print the hash contents. So we'd initialize our iterator. And then we'd loop while the iterator has something else. We'd get the key. We'd print maybe the key value pair using the get function to say here's a key, give me the value associated with it, and we'd just loop like that. And we'll see iterators a lot, right? For different kinds of structures, we can always think of an iterator. But hashes are the first one where it's kind of essential, right? Where I guess we could use them for lists also. But where there's no way to go in and ask for data explicitly, because we don't know, you know, what the keys are ahead of time. So how would we implement this? Right, your hash is implemented in some kind of array. With a key and a value. And there's, you know, some entries in this array that are in use, and there's some that aren't. And there's a deleted flag that doesn't really come into play here. And so if we wanted to just go through this structure and pull out the keys one at a time, we could do a loop, right? We being the person who implemented this code, because we're on the other side of the firewall. We have access to this. We know how the array is set up. We know how big the array is, and so on. So we could iterate through the keys by just running a loop from 0 through the last element, and for each index checking to see if the node is in use. And if it is, then we know that key is another key that we should return to whoever's asking for the keys. So implementing an iterator in this case is pretty straightforward. So we need an evil global. but we'll call it a static so it's not an evil global. Um, so we'll have an iterator position. We'll be nice and started at 0. So to start our iterator, what do? Just initialize the iterator position. And this is the index of the next thing I'm going to return from my next function. Or where I'm going to start looking, right? So, so what's our IT next function do? Start at your current iterator position and just move through and try to find a spot where you have a key. So if we find a spot where it's in use, right, just remember that key value so that we can return it. Update our iterator position to be the next spot in the hash so that the next time we ask for the next key, it will begin after the value that we're returning right now, and then return the key. And if you get to the end of this list, something went wrong. You didn't find any other keys, which means the person probably did not call hasNext. So do something appropriate here. You could return null, you can halt and catch fire, whatever. Alright, what does our hasNext function do? It's supposed to tell us if there is anything else available to be returned by a call to ITNext. And we can do almost exactly the same thing. So start moving through your array, beginning at iterator position. And if we find a spot that's in use, we can say, yes, go ahead and tell the person there is something available. And if we want, we could actually say, let's update our iterator position to be I. Because we know that when we come in here, we're going to start from I and look for a spot that's in use. So we could do this if we wanted to. If you come to the end of your for loop and you didn't find a spot that was in use, then we can return 0. So itPos equals I plus 1. itPos is saying the next time that we want to find an iterator, this is where we start looking. So we initialize it to 0, saying we're going to check this spot first. Let's say the person says, give me the next thing. Okay, we're going to increment I to 1. We find a node in use here. So we're going to return this key. What should itPos be set equal to? It should be set equal to the index of the next spot in the table. So that the next time that we say, give me the next key from the table, it starts looking at this position. Right, one spot after the key that we just returned. So there's nothing magic about this code, right? The goal is really give the user a way to say, hey, give me the next key, right? Which means remember where we were in our array, because we're going to go through the array. We're going to hand back keys wherever a node is in use. So remember where we were in here, and when they want a new key, start from that location, move until you find a spot, return that. If they want to know, is there another node available, another key available, right? Just search from your current location to the end and see if there's anything that's in use. If there is, you can say, yeah, there is another key available. If not, then we say no. And seed the whole thing by just setting your iterator position back to 0. And now I can run this chunk of code as many times as I want. Right? My IT start's always going to send me back to the beginning, and this will loop through everything in my table. You don't want to update your hash while you're in the middle of this, right? Because you'll miss stuff. All right, does that make some sense? All right, let's bring questions for that tomorrow. Bring questions on PA3 tomorrow. Otherwise, we will call it good with hashes, and we will start talking about trees, which is our next big gear change in this course. So binary trees starting tomorrow. All right, I will see you then. Take care.